Hello everyone, this is our next section. Here we are going to design PID controller based on practical observations. Let's start with the first exercise. We have to create a system with these given parameters. So I will do like that. We see that the controller is just one, sensor is just one, so these are simple wires. And then I have to create the system block. So that is a transfer function with these parameters 5 here, 10 and 1 here. And we have a transport delay of 5 seconds. Connect these two blocks. I am going to use a step excitation. It's important that we start from 0 time. I connect these blocks. And I use a scope with 2 input channels. One is for the input, one is for the output. So then I look at the scope and I see, the simulation time is not enough. So I set the stop time to 100 and I see what happens. Then I see that, okay, now the signal is in steady state. We are happy. And with this Ziegler-Nichols approaches, what you don't know is the exact transfer function form. You have only observations. So what I am going to do is that I hide these blocks. I select these two blocks, create subsystem from section. So we really see an input-output relationship and we don't know what is inside. Okay. And what we have to do with the open loop technique is here in this PDF document that we will use simple open loop step response. We analyze this, so we have to read the static gain, the dead time, and the dominant time constant. So I will do this based on this scope figure. So what we can do is, for instance, we print this figure. So file print figure. Then you get a new figure. It's a figure object. Here you can insert objects like lines. And what we see that this background is not so nice, but we can change all the style parameters. So I go back to scope, tools, where was it? Tools, view, style. Here. And here I can change axis colors. For instance, here I will use white. For the tick labels, I will use black. For the line, you can change also here the line parameters like this. So it looks better. Then I can go again here to file, print figure. And we can change also other parameters because here the problem that now we don't see the labels here. So I go back, then view, style, and I can change parameters again. Like this. It looks much nicer. Okay, so again, print the figure. That looks now acceptable. The first step is that we have to estimate what is the static gain, Kp, in this table. We can see immediately that it's 5. And to estimate the two other parameters, you can do many things. I will use the recommended graphical technique. So I insert different lines here, lines. So I have a line, a straight line for the static gain, for the final value, here, and I have to draw here a static line on the tangent. What we can still do, because this resolution is not so good, we can change this. For instance, you can double click and you can go for grids and activate the minor grids. So X minor grid, Y minor grid. So it looks already nicer. So I insert a line. So it's a line on the tangent. Again, here we don't know the exact parameters of the system. We estimate based on the step response. Here we don't have noise. In the next measurement, in the real labo exercises, we will have real noise with real systems. So it's just a little bit training how to do these things. So here I have a tangent line. Then at the crossing of the final value and the tangent line, we need to also project a line here down. So I make a little bit nicer. It's something like this. So I take a line and I project this down. Okay, excellent. And here we have to read the two parameters. L is for the dead time. Here when I see it's around 5. And here what I read is that this is around, I would say 16. This line, and I have to subtract the dead time, so it's 11. So T is 11, L is 5. I have these two parameters, and now I have to design a PID controller. Here we see the parameters for the K, for the integration and differentiation time, and here we have the structure what I recommend to use. So we have to implement this. I go back. I'm a little bit lazy, so I'm going to copy paste the things, what we see here, like this. And I will augment these items first with the feedback junction. So plus minus, here will come back the signal, the output signal. Then we will have to do this structure. So K is a gain. Then here we have a simple line. Then we have the integrator and the differentiator. So here we need also junction point, plus, plus, plus. You can also use some object instead of add object or any other compatible object. It doesn't really matter. So I have the line here. Then let's start with the integrator. So it's 1 over the integration times S. So this is a transfer function. I connect it like this. And now I have to make the integration form. So 1 over this value should be 0. And now we have to type here the integration value. And we see that the integration value should be 2 times L. L was the dead times, 2 times 5. It's 10. But of course I can write also like this, as you wish. It's up to you what you prefer. Okay, excellent. And we have the D term. It's also a transfer function. Excellent. Now I connect the rest of them. And here I will measure the error signal. So it's here between the reference and the controller. And I will check what the output is. And of course, I can give names for these signals. So reference, error, sorry, and process value or output as you wish. Okay, and now we have to do this TD term. And what we see that here it should be simple 1. So it's TD times S over 1. It's TD times S. And if you remember from the first lesson, there is a problem. We cannot implement an ideal differentiator. So here I put the parameter 0.5 times L. L was 5 seconds, the dead time. So it's 2.5 seconds. And when I try to do this, then you will get an error that the order of the numerator is larger than the order of the denominator. So the system is trying to predict the future. It will not work. So what we can do also in practice is use that we apply an additional first order system. This was explained in the previous presentation. So it's a first order low pass filter to get rid of the high frequency noise components. That will be very, very important for the next labo exercise. And we can implement this. So TD is the idea block, and we multiply this with a first order low pass filter. So this that is 1 times 1 over the time constant S plus 1. So it's very simple. And what we use in practice is usually 10% of this time. So instead of 2.5, we say 0.25 and 1. I can enlarge it and you will see this better. So this term you can split it to 2 terms, 2.5 S times 1 over 0.25 S plus 1. So it's a combination of a first order low pass filter plus this D term. Okay, excellent. And the last remaining parameter is the gain here. And here I can just use simple table. So 1.2 times T was 11 over L was 5 over KP was 5. So you can use also formula there. I try to make it a little bit prettier. Like this. And now we can look at the output. And what we see in red is the output, and in yellow is the error. So I can activate here the legend, so you can also see this. And what is expected, the error level goes to 0 with the PID controller. And what we are not happy here is this response. So we have a lot of oscillation. And usually this Ziegler-Nichols is used as the first initial step. Then you can fine-tune the parameters. So when you see that you have too much oscillation, then for instance, you can change the gain value, reduce it. So instead of, let's say 11 or 1.2, I can put here 1.1. So I reduced. Then I can fine-tune the elements. And we can see that we have already less oscillation. And I strongly recommend that you play around with these parameters. This is also what you will do in the next exercise. Okay, thank you for your attention.